Hello, everybody. Good morning, good afternoon, good evening. Welcome. Depending on whatever time zone you're joining us from, I'm glad to have you on board. I'm Kenneth Wong. I'm Senior Editor for Digital Engineering 24/7 and also the usual host of this webcast series. Now, today's episode is called How to Design, Validate, and Optimize and Manufacture Latticed Parts with 3DEXPERIENCE CATIA. All right. And before we begin, just to make sure that you get the best possible experience, let me give you a few tips, okay? I want to remind you that if you have questions for today's topic or if you have questions for our panelists, you can type the question into the Q&A box at any time. I assure you that we'll address as many as time permits, and the ones that we cannot address, we will work with our panelists to make sure that you get a written response. You can also download a PDF copy of today's slides and check out the resources related to the topic to the resource list to the left side of your slide window. If you experience any technical problem, please visit our webcast help guide by clicking on the help ? Icon at the bottom of the console. If your slides are not advancing, you might want to try pressing F5. Usually you refresh the browser and that solves a lot of the problem. So what are we talking about today? Today we're talking about a special kind of design. You might have seen it. It's called lattice. They're very complex structures, and to do them traditional way might not be very easy. So our presenter is going to show you a simpler, easier, better way to create them, validate them, analyze them, and optimize them. Let's meet our speaker. Daniel, welcome.
Thank you, Kenneth. Thank you for the introduction. Hello to the audience. I hope you will have fun during this 40 minutes or 45 minutes. It's my pleasure to be with you. I am part of Dassault Systèmes. I am in the CATIA organization, and I am, let's say a CATIA technical fellow. Okay, I started computer-aided design, computer-aided manufacturing just 40 years ago, and it's a pleasure to be with you today. So let me start the journey. So thanks a lot for attending, and don't hesitate to ask questions in the special widget on the right side of right corner of the screen. So let's go. The agenda of today is very simple. What is a lattice? Okay. The second topic is what do we need lattice for? Okay. And then I will introduce what the 3DEXPERIENCE from Dassault Systèmes provide as solutions to design, but also validate by simulation, by FEA, finite element analysis, and manufacture this very, very complex structure the very first time, remember that this structure is so complex that there are not many ways to manufacture it, only 3D printing, okay? And we will finish with the conclusion. So let's start the journey. I will ask from time to time what is the view of Kenneth regarding what I just showed. So let's go. First one, what is a lattice? In fact, it's very simple. Huh? It's just a structure made, created by a repeated pattern. Sometimes it's called cell, along multiple directions. If you look at this slide, you will see a type of pattern. It's made of 3 cylinders, which are just orthogonal. And then we can repeat this pattern along 3 directions, X, Y, Z. This is the orthogonal repetition. We can also repeat this pattern along a radial direction. You can notice the difference. The orthogonal repetition, the cell is exactly the same size. When it's a radial repetition, depending on the position of the cell regarding the center of the rotation, it's bigger, okay? So it's not the same size. That's just some particularities that you have to take into account, because sometimes either one or the other is the preferred way of repeating this pattern, okay? What is very important is that a lattice is not made only with simple elements such as cylinders or cone, okay? It can be, and I show just here some example of so-called BCC cubic, BCC FCC, crown, diamond, dot. You are probably more familiar with honeycomb. There are many other, okay? So this is the type of pattern or cell that we can replicate. Very recently, even if those guys have been created or found long time ago probably 30 years ago, I think by a guy from the NASA, thanks to him, the so-called TPMS, triply periodic minimal surface. The most famous is the gyroid that you can see on the lower left corner, okay? But there are many others, like Neovius, Lidinoid, IWP. It's not by chance. All those guys, those TPMS or the BCC cubic or the diamond or the honeycomb, they have a particular properties that you can take into account if you select one of them. Some are more, let's say, more appropriated for parts which are compressed. Some are more appropriated for parts which are stretched. Some are a better choice if your product will be warped, okay? So you will use the right combination or the right TPMS depending on what you want to do, okay? Is it clear for everyone? So let's go now. What is it used for? Before that, I forgot it. Thanks to 3D printing, you can really produce and manufacture actually very, very complex shape. And the normal regular lattice is just the same pattern, except if it's radial, is replicated. But sometimes you would like to follow the outer shape of your product. It's what we see here in the middle of the screen. It's called conformal lattice. So the lattice structure is following the shape of the outer boundary, okay? And of course, you can also go even further by saying, okay, let's say the pattern will be big at the beginning, but very, very small at the end. It's what you see on the lower left corner. But you can also decide that the thickness, so the density of the material is also varying, okay? So as you can see, it's quite complex. You can have very complex shape. You can have very complex, let's say, replication, not only orthogonal or radial. And you can also have varying thickness or varying dimension. Okay, let's go. What is it used for? In fact, you have many, many usage of lattice parts, okay? Remember, only 3D printing can actually, today at least, manufacture those very crazy shapes, okay? The very, very first use was, and it still is, to reduce the weight of a part, okay? If you look at the part which is on the upper right corner, we wanted to decrease the weight, so we added cavities. Here it's open cavities, but it can be closed cavities as well. And we fill those cavities by a lattice structure. Most of the time, the lattice size, the diameter, for example, if you are talking about cylinder, the user can be asked or prompt to type in a diameter. But in fact, what he wants to gain a certain weight. So most of the time, the input is, okay, I would like to gain 96% of the weight, okay? Just have 4% of weight inside those cells, okay? And the software will define for you the size of the lattice that you are using, okay? Remember, very first usage, reduce the weight of a part. But then it has multiple other usage. For example, the lattice structure, depending on the material, depending on the type of lattice, can also absorb energy, and it can also absorb vibration, okay? So you can imagine using those type of lattice, for example, for a sneaker sole, a running sneaker sole, okay? Or some, let's say, cushion inside a car seat, whatever. So this is also a very nice property of a lattice structure. There are some other usage. Which one is very important? You can also use them to develop and very, very efficient heat exchangers or heat exchanging devices. Why so? Because by using those TPMS, especially the gyroid, we will be able to produce a very, very efficient heat exchanging system, but the most important, very, very compact. You know, one of the challenges of the industry, especially oil and gas, but not only, TNM, aerospace and defense, TNM standing for transportation and mobility, they are looking for not only for weight reduction, but also for size reduction of the various components, okay? So you can not only create very efficient heat exchanger, but those can be very, very small and very, very compact. Okay? Something which is in use, in fact, since many, many years now, probably 6 years or maybe even more, is to use lattice structure in life science. Why so? If you take this type of hip prosthesis that you see in the middle of the screen here, the upper part of the hip prosthesis need to be integrated into the bone, okay? So to facilitate the what's so-called osseo-integration, sometimes people are calling it osteo-integration of the bone, you can use this type of pattern and the bone will much more grow inside this very, very strange, but very natural shape as well, okay? Finally, you have also customer or company using just lattice to make very fancy, very aesthetic shapes, okay? It's not only for weight reduction, it's not only for heat exchanging, it's not only for osseo-integration, sorry, but it also sometimes we have very, very nice and cool shapes, okay? Like you can see on the lower part of the screen. So, Kenneth, what is your view?
I really like the idea of using weight as an input, you know, because if you ask somebody to actually change the diameter of the cell itself, it's a hit and miss, right? Because you can't really hit your weight target. But if you really use weight as a target input, that's perfect, because most of the time that is the reason people are using lattice to begin with anyway.
No, perfectly right. And the good news is that CATIA can do it. But we are probably not the only one, okay? Okay, let's continue. So now that we know what is a lattice, that we know what the lattice is used for, let's have a look on how 3DEXPERIENCE from Dassault Systèmes and in CATIA, but not only, we can design lattice parts, okay? How we can validate them by finite element analysis, but also manufacture them. Let's start. Why did we develop a special product for lattice design? It's very simple. If you look at the part here, which is a light blue part, it's just a very simple part. A cylinder, 300 millimeters height, 300 millimeters diameter, thickness of 1 millimeter, and the lattice cell is 4.5 millimeter by 4.5 by 4.5. If you count, I count it for you. we get 225,000 cells, okay? If you use the actual technology, which is in most of CAD system, like CATIA, we are using exact boundary representation. There is no chance we can use this technology to actually represent this type of geometry. Looks simple, but it's crazy, okay? So we had to develop new data model. It's so-called implicit modeling, where it's just equation, which are this particular part here in CATIA, with those 225,000 elements, is probably less than 1 kilo-octet. Very, very simple stuff, okay? Because it's just equation. Of course, we will not print equation, but this will be the next slide, okay? So what we have to do is to be able to quickly design those shapes, to visualize them, pan, zoom, rotate, to be sure that the input are the right one for our design. We would like to also quickly, with a very light model, validate by structural validation, so by structural analysis, sorry, but also some other analysis, you will see. And once everything is fine, just once everything is fine, we will convert the implicit model by an explicit tessellated boundary representation, a set of triangles, because today the actual 3D printers are only able to read this type of information, okay? So, new data model based on implicit modeling. You get something very fast, you can visualize it very smoothly, you can validate by FEA, and then just at the end, you will convert to get a very nice watertight, clean mesh for the 3D printer, okay? So let's start. We have two ways in CATIA to actually create those lattices, either this orthogonal radial replication with bars or TPMS, or you, as a user, define your own algorithm to define this 1D graph, this set of the structure of the lattice that you will use. So let's have a look at the first video about lattice design. Can we launch the video? Thanks. So what you see here is a very simple part. And what I'm doing right now, I am just defining the cavities I would like to fill with my lattice structure. In the first example, we will use only bars, cylindrical bars, okay? So the UI helps you to very quickly define the cavity, closed or open cavity. You can define as many different types of lattice structures that you have cavities, or use the same. You can combine radial lattices, or orthogonal lattices. You can, of course, define either the density you would like to reach or the dimension of the lattice, the dimension of the cylinder and the diameter of the cylinder. You can select among the various proposals, BCC, whatever, honeycomb, cube, crown, the type of lattice you would like to use. And once this is done, you can, as you see, very quickly display the result. So when you are in the light representation, those lattices can be shown as nothing, or bars, just line, or really cylinders, but it's still a light representation, okay? So once this is done, you just either also select the position of the lattice by a local coordinate system that you can rotate after that. And you see the result here. It's still very light model, okay? It's still very, very small, probably 100 kilooctave for this, kilobyte, sorry, for this one. And now the idea is to run, why not, a simulation. The good news is that once I go to the simulation app, the lattice is known as a special feature, and the finite element tool will, let's say, create automatically a 1D beam as a finite element model for each lattice bars, okay? So very quickly, you can create a mesh made of the lattice beams, the 1D beams, and for the outer shape, the outer body, you can select either tetrahedra or shell mesh, depending on what you want to do. So this is what we show here. So we can do that. And now the idea is, okay, I have my lattice part, I made a simulation, but what I would like to do is to optimize what are the best dimension, what are the best nature type of lattice, what are the best diameter, size, and so on. And we do what we call a parametric design study. So we will give to CATIA a set of a range. So let's modify, for example, let's investigate, for example, the diameter from 1 to 3 with a step of 0.1. And you can then run all those simulations very, very quickly. In this particular case, we have 60 of them. And we will run this parametric design study. So create 60 different variants of your part. And to select the most appropriated variant, we will then couple this design with a structural analysis. So we are defining what are the parameters of the lattice we would like to optimize, but also, in the same time, the response variable. Let's say I would like to minimize my weight. I would like to minimize my von Mises stress. I would like to minimize the displacement, okay? So those are the design, the response variable that will be used to select the best solution after having run a structural analysis. So this is the various geometries that you can see. So 60 of them. So it's quite fast and it's not accelerated. It's not an accelerated video. Then I will run my structural analysis for each variant. And CATIA will tell Simulia, which is our simulation brand in Dassault Systèmes 3DEXPERIENCE solution, will also propose to you what is the best solution from your design response variable, sorry. And then you can select among the ones that are on the left side, you can select maybe 2, 3, 4, 5 of them, and you will have then you can deep dive into each of them to see which one is the best, is your final result. Okay. And still, we are working on the implicit modeling definition. So we selected 4 of them, and then we feed the model, the CATIA model, with the parameters that have been optimized by the parametric design study. And now, just now, we will convert the implicit model into an explicit tessellated boundary representation. We will also add fillets between the bar, and more important, fillets between the bar and the outer shape. So not only it's stronger, but it's also easier to print. Can we launch the second video?
Your creativity with lattice structure design driven by algorithmic in 3DEXPERIENCE. We start by generating our own structure of lines with CATIA visual scripting to be reused in CATIA lattice design. In this example, the lattice thickness will be driven by a specific distance law for a gradual effect. The new lattice specification operator is now available in the design sequence editor, with CATIA lattice design as prerequisite. This operator will publish a specific lattice feature as output to be reused for lattice generation. Here we use a list of lines, a list of radius, and published volumes as inputs of the lattice specification. Then, we switch to CATIA lattice design application. A new lattice definition can be created from the published result of CATIA visual scripting with an associative link. Volume, cavities, custom lattice structure and thickness are automatically reused to generate the detailed geometry. Lattice result is also merged with surrounding volumes. This new connection between CATIA visual scripting and CATIA lattice design opens up new design perspectives. And generated lattice can be directly and natively reused in simulation or manufacturing process of the 3DEXPERIENCE.
Okay. So the TPMS in CATIA for now, in 3DEXPERIENCE CATIA for now, we have a couple of them. So like the gyroid, like the Neovius, like the Lidinoid, like the IWP, Fisher core, and diamond. What I just want to emphasize is that, as you see, the lattice is not just a surface. It has a thickness. And TPMS has a thickness. And TPMS are very, very particular geometry, where in some area, there is multiple normal. So if you want to compute an offset to get the thickness, it's not that easy. So, and we really ensured when we created a TPMS with a thickness, that the thickness is as constant as possible everywhere in the geometry. And that's not that easy, but CATIA can do it. Okay, let's continue. So as I told you earlier, it's very efficient for heat exchanger, but it's also very, very efficient for radiators. Most of the time, those radiators are made of ribs, which are parallel each other, okay? But if you use a gyroid, it has been proven that it is much more efficient. So you can also maybe make them smaller. And it's quite important. Again, size is important. The small is beautiful, okay? So now, what is also fun with TPMS, especially gyroid, it is very, very adapted to the powder bed fusion process. Why? They are self-supported. Whatever their position in space, whatever the position of the part and the slicing, you don't need extra support. Okay, it's self-supported. If you look at the lower pictures, if I have bars, my laser will move from one point to another because the intersection of the bars, depending on their orientation, of course, and the slice might create some spot. So you have to lace from one spot to another, which is not very efficient. If you use a TPMS, a gyroid, the intersection of the plane with the gyroid is a continuous curve. So the laser will always move continuously. So it's much more efficient from a production, manufacturing point of view. And something which is also cool is that if you have powder, you might imagine that you have a lot of powder. This toboggan type of shape evacuates the powder much more easily. So it has a lot of nice properties. And what we measured is that if you use TPMS rather than bars, you might reach the same gain in terms of weight. Okay? So it's really a very cool geometry. Now let's have a look at very quickly how we can manage those TPMS in CATIA. And we will start the first video of this slide. Here it's a very simple stuff. We just want to lightweight this part. So we create a cavity in the center of the part, and we will select a gyroid type of lattice structure. And we define the shape, we define the dimension, the thickness, very important. And then we will be able to create it. But before actually printing the part, we would like to run a simulation. And in this particular case, we'll not use the light representation. We'll use the tessellated representation because we want to run a simulation which cannot be used by an idealized finite element like a beam. Okay? So we really want to mesh everything. So here we use a tetrahedral mesh for the whole part. It's a stem mesh. It can be, of course, small elements because the lattices are very small, but you can do it. And you can run any type of simulation where you need those tetrahedral elements. Okay? This is also possible. So you are not forced, again, to work, for example, with a 1D beam for the cylinders, but you can also run a tetrahedral mesh inside the cylinder, depending on the actual physical phenomena you would like to simulate or validate. Can we launch the second video? In the second video, you will see a very simple example of how you run the lattice command in CATIA to do this small heat exchanger. You can see you have the cooling, the fluid to be cooled down in blue, and the fluid which is cooling down the other one in red, okay? The one which is warm. So what you can see is that we really take care of avoiding mixing those channels. Those channels, the fluid should not be mixed, between the cooled liquid and the cooling liquid. And this is not easy. And you also need to take care of where is the lattice structure versus the input and the output. Otherwise, maybe the fluid inside the heat exchanger will not go properly at the right location. And that's not easy. And it is also taken into account in the CATIA feature in 3DEXPERIENCE. And now can we launch the next and last video? In this particular video, we are using TPMS to do a spine disc replacement. Okay, so this is the shape of this prosthesis, and we will fill the shape with 4 different types of TPMS. So I guess you got the UI of CATIA. You select the cavity. There are 4 of them. You select for each of them the nature of the TPMS. And what you can see also is that it's extremely fast to display on the screen the result of your selection of type TPMS. It's because in this particular case, for the display, we are using the GPU of your laptop or desktop, not the CPU. So it's extremely fast. It's a high quality. Once we will compute it really, then we'll use the CPU because the CPU is much more accurate today than the GPU. GPU is very, very good for display. So now the user knows that the lattice is selected as the proper one. He can, of course, modify it. Everything is associative. If my part is changed, all the lattice structure will follow according and be modified according to the modification of the shape. Now I go to my finite element analysis application on 3DEXPERIENCE, and I will want to run a simulation. Before that, I will create my finite element model. In this case, not like in the first or second video, we will not use tetrahedral mesh on the explicit tessellated representation, but we still use the light representation. And 3DEXPERIENCE is smart enough to create automatically a shell element, shell mesh for the lattice, the TPMS, and a tetrahedral mesh for the outer body. Of course, the shell elements are assigned with the right thickness, the one that you selected for your TPMS lattice. And then you can run the simulation because we tie together both finite elements, let's say a structure. So you can, again, in this case, validate very easily a complex shape. And at the very end, which is shown here, we convert the implicit model into a very, very nice watertight mesh to be sent to the printer. This is what I was mentioning regarding that we take care about where are the lattice structure versus the input and the output of the fluid. We take care about not mixing all those guys together, the cooling circuit and the structure to be cooled down. You see here, there is for sure the fluid will go into and go out, go in and go out. And finally, you see the quality of what has been created by CATIA. This looks easy, but it's not at all easy. Huh? And finally, you can also do radial TPMS lattice structure. So it's really depending on what type of heat exchanger you are looking at. So very high quality. And I think that's it for the last video. So let's move forward. Let's go further. Now I have my heat exchanger, but I want to be sure that first of all, the heat exchanger is giving the expected efficiency. And then, as I told you earlier, only 3D printing can manufacture the job. We want to check that there will be no issue during the manufacturing process, during the 3D printing. So this is the part. So what we will do, first I showed you already on the spine disc replacement, but we'll do the mesh. Then we'll prepare the scenario, the FES scenario, boundary condition, load case, and so on. And then we will analyze the result. What is important to remember is that if you do this type of analysis, it's important to use the best finite element model depending on the analysis that you want to do. In this particular case, the thickness of the part, the thickness of the TPMS, we will use tetrahedral element because they are the most appropriated for that. But for the fluid, for those who are familiar with CFD, for the fluid, the best element for fluidic analysis is hexahedral. So you can combine both the hexahedral element for the fluid and the tetrahedron element for the solid part of your heat exchanging. So, and then you just have to select to run the simulation, and you get the fluid and the solid temperature slice. You can also the streamlines, what is happening in your heat exchanging device. You can also get, very important, the fluid total pressure with the streamlines. And finally, the velocity to check if the pressure drop at the output of your heat exchanger is still acceptable. Okay? So that's what you can do. You can not only design, but you can not only validate the structure, you can also validate the efficiency of your actual heat exchanging device. So, and in the 3DEXPERIENCE platform, we have something magic called Process Composer, where you just type in the input. For example, you would like to optimize, let's say the gyroid dimension, thickness, and orientation. What are your, let's say, response variable, the fluid velocity, the total pressure, and you can run a loop and check which one will be the best and optimize the parameter of the gyroid. So let's make a first loop, a second loop, a third loop. So in this case, I just optimize the geometry, my design, to match my expectation versus how will behave the part in service, product in service. How efficient is my heat exchanging device? But now I have to produce it. I have to manufacture it. So in 3DEXPERIENCE platform, this is what, it's a small picture, but what you can see here is that this is my build tray. This is multiple parts I print at the same time in a batch in my shop floor. I also add coupon, and I can simulate what is happening during the printing process. So I do a thermal analysis. I can couple the thermal analysis with a mechanical analysis to get a thermomechanical result. So I can predict the distortion of those parts. Okay? Why so? I can do the same on my heat exchanging device. You can see here the residual stress. You can also see the distortion of the heat exchanging device. You can see on the side we have some issues here by printing. Of course, not that big. Okay? And now, as we were able to use Process Composer to optimize the design, we are also able to use Process Composer to now optimize the parameters of the machine, the laser power, the recoater speed, the type of support, this is more geometry, and also versus, for example, the gyroid dimension and the thickness. So we can run now a manufacturing process to double check that, optimize maybe either the geometry or the more than that, the parameters of the printing process to be sure that the part will be actually printed right. If for any reason you cannot manage to reduce enough the distortion, there is a magic tool in CATIA called virtual to real shape morphing. Virtual to real shape morphing can take the simulation, the prediction of the distortion, and compensate the geometry. So it goes in the opposite side. So you will deform the part to get a wrong part, but a final product perfect regarding the specification. This can be done by using the simulation prediction, or if you are not sure, it's a new material, it's something new, you can scan the first printed part and import the scan data into here and use the scan data as it was a result of prediction of deformation by simulation. Both processes are valid in CATIA. And the beauty of the platform is that you can do multi-physics optimization. So not only you are optimizing the heat efficiency, the heat exchanger efficiency, the printing process, reduce the distortion, and again, you can do really multi-physics optimization in the platform. That's the beauty of 3DEXPERIENCE. Here we are. This is now the last slide for the conclusion. After my conclusion, I will let the mic back to Kenneth. I talk too much.
Not at all, not at all. You're saying very interesting things, so go ahead, please.
As a conclusion, thank you, Kenneth. So as a conclusion, Lattice is in productive use today. Huh? We are using Lattice, the industry is using Lattice for a long, long time, especially for the prosthesis. It's also in productive use for industrial design, but it's not mass production or customized mass production like for the prosthesis. It's more single pieces in a car or in a plane or whatever. But it's a promising technology, huh? But it's not that easy to manufacture. That's why it's good to rely on simulation or on the process, like I showed you on the printing process. But my recommendation is don't wait. Go for it now. Kenneth, what do you think?
You know, when you are showing the switch between CATIA and Simulia, I noticed the fact that you talked about how in the display you could actually just use the formula so that the model is very lightweight. I think that's very important, because if you have a fully rendered model, it slows down the computer a lot. So, but when you switch to Simulia, of course, then you do need the full featured model to be able to run simulation. So the ability to do both ways is very important, I think. Yeah.
Yeah, I fully agree. By the way, it's not that easy, you know, to compute a good shell mesh of a TPMS in contact with the outer body, which is tetrahedral mesh, and have a consistent, very valid finite element model. It's not easy, but we took particular attention to get the result properly solved.
Mm-hmm. That's right. Okay. Perfect. Yeah.
So I think we are almost on time.
So, we are definitely on time.
First of all, I would like to thank you for your attention. I hope I was not too whatever with my French accent. Thanks a lot to Kenneth to help me on that. Maybe don't forget that we have a nice community, Dassault Systèmes community. In fact, we have two of them. One is called 3D CATIA user community. The second one is called ModSim Community. Not only you can go there, it's very simple. You just ask for a passport, you give your email, you get you enter a password, and you get the information. Then you can also chat with me. I am part of this community. You can chat with my peers, you can ask questions, you can get documents. So please have a look, join those two communities. It's free of charge, okay? The digital engineering people will also provide you, if you want, the PDF, the exact same document that I just showed you right now. If you want the videos, because it's a little bit more heavy, in the first page you have my email address. You don't hesitate to send me an email, or you use the community to ask for the videos. Any question in the chat?
We have quite a lot, Daniel. So let's take a look at it together. But maybe we can start with a couple of questions that came in from people who were registering. The first question, I think it may be simple for you to answer, is can you use lattice to form airfoils and hulls? That's the first question from the registrant.
Yes and no. You know, the hulls are quite big. In fact, we use that already, but it's not really known as lattice. If you take composite part, in composite part, you have honeycomb inserts, okay? So those honeycomb can be assimilated as lattice structure, but as you know, it's quite big, okay? For a foil, a foil is still big. It's still big, maybe we are missing is the actual way to produce it. No, a foil may be 3 meters by 2 meters dimension. So we have to find out the right machine to actually put the lattice. So for me, so far, at least from what I know, there is no lattice inside the foil. And in the hull industry, it's more the use of honeycomb in composite parts.
Very good. Second question also from the registrant. This one is rather general. How do you think artificial intelligence or AI will influence generative design iterations?
I mean, I think for the AI, there are two ways. By the way, Dassault Systèmes is working a lot on that topic. You will see some new stuff coming very soon in the portfolio of Dassault Systèmes solution on 3DEXPERIENCE. But there are two ways, in fact. Either you can use AI to just analyze multiple data, multiple parts that you produce in the past, and to correlate the result of the simulation with the design itself. So if you have a similar design, you might quickly get an idea of what will be the distortion or the efficiency. And you can also, in this case, use the appropriate lattice structure. So you will win time, okay, by using AI. Another way of using AI might be to, again, put into the system the know-how of the experts and reuse this know-how as much as possible. But it's still a long journey. Multiple people are working on different topics on AI. It's a very, very, it's a very nice topic. I like that. And you will see probably very new stuff coming very soon.
Very good. Daniel, I'd like to also give you a chance to scan some of the newer questions that came in. And while you're doing that, let me go ahead and repeat and remind the audience that they have two specific communities that they can join if they have more questions, or if they want to enter a discussion, possibly directly with Daniel in the written form. And that is a CATIA community and also a ModSim community. So either one of those will be good for you to be able to talk about your lattice design issues and problems. Okay, Daniel, what do you think is the next question you want to tackle? Do you see any good ones you want to tackle?
Let me check. Let me check.
No problem. Let's take a look at this together here. There are a lot of good questions. Very specific questions would suggest to me that a lot of the audience members are actually thinking about doing some of the things that you're showing, which is really good. Yeah. And audience, if you have more questions, feel free to type them in. Daniel will address them as time permits.
I'm just checking. So regarding, benchmark analysis, problems for lattice structures that are publicly, let's say, shown, it's, every single customer is using lattice. To be honest, lattice, we are still at the beginning. Most of the industry, except life science, except fancy shape, they are still at the research level. they try to see what is the best lattice. At least it's my point of view, okay, my experience. So they are doing a lot. They don't want to publish their results because it's like IP for them, okay?
That's right.
And they are doing coupons, they are doing multiple things to be sure. And so they are not, for sure, some university everywhere in the world made some public comparison between lattices, whatever, what is the best TPMS? Is it gyroid or Schwarz for a spine disc replacement? There are some paper, I found some paper, but it's still the beginning. Let me check if there is another question.
Very good. Let's take a look at some other questions and see if there are good ones that you'd like to take. Yeah. Yeah, I'm pretty sure, like you said, that a lot of the university research labs are probably doing a lot of research on the effects, pros and cons of different type of cell structures. Maybe they're just not in the public realm yet.
Yeah. No,
what do you think?
I have one question because I can because it's a very simple. So Mike asked me, is conformal latticing available with GDR integration? For those who are not familiar with GDR is a trigram for our CATIA visual scripting tools that I showed you on the Eiffel Tower. Okay, and so the answer is yes. So conformal latticing can be done today with GDR, but you will have to develop your algorithm. It's your job to develop the algorithm. What I can tell you is that in the Lattice Design CATIA app, we will also do conformal latticing this year, but it's not yet available. But it's coming soon.
It's good, something to look forward to. Okay.
Yes, this is also complex.
Let's take a look at some of the other questions. Yeah, which one is good for us to take on the air, so to speak?
Let me check. Let me.
Some of them has to do with the comparison of different types of lattices, or some of them have to do with how you would change the cell structures for finite element analysis. What do you think, Daniel?
Yeah, let me check. Yeah. As I told you, there is mathematics, there is the universities. We are still at the beginning, and still people are just trying.
Understand.
They try a gyroid. They try. Very important parameter in the gyroid is a thickness. Okay, so they try multiple thickness. There is no real. It's still an ongoing journey.
Experimental phase.
There is no real statements, true statement. It's still some people are still looking, still researching, especially for the heat exchanging stuff. Okay, but the good news is that we really try when we develop something not to just produce geometry, but to produce geometry which is feasible. I was mentioning this offset of the TPMS of the gyroid, the fact that we take into account where are the input output of the fluid to be sure that the two channels are not mixing, which is not that easy. It's very complex shape. You might have some issue, and in some Boolean operation, you might create some leaks. Which so this is really what we would like to do, and we are doing, by the way. It's why we are maybe not the first on the market. But we provide a very robust solution.
Sounds good. Yes. Yeah. Take a look at that. There is some latest questions that came in as well, and take a look at it and see if you would like to address any of them on the air, so to speak.
Yeah. Shyam is asking about how efficient is the topology optimization in CATIA. Here, I did not talk at all about topology optimization because lattice is just. You can optimize the size of the lattice by depending on the loads and boundary condition. But the best way to do it is more to use we have dedicated solution. It's called structural generative design and fluidic design, generative design, to do topology optimization for both structural phenomena or fluidic phenomena. So we have very, very nice tools which are fully integrated in CATIA. So it's really a tool for designer with a UI for a designer. It creates expert result, but for a normal, let's say, mechanical designer that I am. So, and if you go to the community, you will see there are a lot of topics about this one. The trigram are SGD and GDF for structural generative design and flow-driven generative design. It's extremely efficient because the engine is very well known. It's robust. It's called Tosca. But in topology optimization, what is the most consuming time is not really to do the optimization. It's just CPU, you run it on the cloud, why not? It's to reconstruct the CAD model that will be used to do casting, to do forging, to do plastic injection molding, maybe the funny shape that will be 3D printed, but it's a very particular case. You need a lot of time today to reconstruct a good CAD model from the result of the topology optimization, which is a lot of time, very, very crazy. The good point is that CATIA is extremely good for that. Extremely good. Please have a look if you are interested.
All right, very good. Daniel, if you don't see any more questions, I mean, some of the questions you might want to address them in writing form because they're very specific. But if you don't see any more questions that we should address on the air, perhaps we can go ahead and start to wrap up. Is there any more questions that you want to take? If not, you can perhaps give the audience maybe one more reminder about the communities that they can reach out to, and then we'll wrap up.
Yeah. So no, I don't see particular topics. Thanks for, by the way, thanks for attending. Don't hesitate to join the CATIA user community, https ghost.3ds.com/CATIA, and also the ModSim community. ModSim is, of course, more focused on modeling and simulation. So if you are an FEA stress analysis geek or a CATIA geek or SolidWorks geek or whatever, you can join both. ModSim is more if you are really interested by finite element analysis combined with CAD. So I would just want to thank Kenneth and the organization, and I hope you enjoy this webinar. And I really encourage you, if you have more questions, to use those community, but also to have a look at CATIA, what CATIA can do. You know, CAD modeling is not a commodity. People say, oh, everybody can do CAD modeling. No, it's not true. No, when I started 40 years ago, the most complex things when I was a young, tech sales in 3D was to create fillets, to create offset surface, and to create draft. And I can tell you that still today, the most complex things to do are fillet, are draft and offset. But now we can also do super complex things like this lattice structure, which was just impossible to just even dream of 40 years ago. Thanks a lot. Have a great end of day. And it was my pleasure.
Thank you very much, Daniel. It's our pleasure as well to have the chance to introduce you and give our audience a chance to see how lattice structures can be designed and optimized and analyzed as well. I want to also thank Dassault Systems for making this live discussion possible. I also want to thank you, of course, and the audience for spending their precious time with us. And let me not forget also that we have a production manager who works behind the scene. Steve is his name, and he makes sure that we look good and sound good and everything runs smoothly on the air. So thank you very much for him too. Until next time, I'm Kenneth Wong for Digital Engineering 24/7, and we are out.